We'll now talk about the relationship of the Laplace transform with respect to continuous time Fourier transform. Let's remind ourselves what is the continuous time Fourier transform definition. F of xt. Given xt, the continuous time Fourier transform equations look like this. It is an integration from minus infinity to infinity with respect to time multiplied by e minus j omega t. Now, you'll see that the only difference with the Laplace is this is e minus s of t. And if we remember what is s of s is actually is equals to e minus sigma plus j omega. And then there's a t here. So in fact, this equation looks very much like the Fourier transform. The only additional thing we have is the word sigma over here in the Laplace transform. If we set sigma equals to 0, then actually the Laplace transform is equals to the Fourier transform. This is what the slide is trying to say. So this is one way we can think about it. Now, the other way to think about it is that if we are given x of t, and before we perform the Fourier transform, we multiply by a signal e minus sigma t, then the Fourier transform of this signal x of t multiplied by e minus sigma 1 of t, isn't that equals to the Laplace transform with s equals to sigma 1 plus j omega. So that is another way to look at it, is that we can look at it two ways. One is that the Fourier transform is the Laplace transform evaluated with sigma equals to 0, and the other way is that we multiply by the signal x of t with whatever sigma 1 that we are interested in, and then take the Fourier transform of it, and this is actually equals to the Laplace transform with s equals to this variable. Now we are going to see a nice picture of x of s, and we are going to take a look where sigma 1 is equals to 0. Let's first give you a representation of x of s. It will look normally like this. It is a polynomial with respect to s, and s is the entire, so this is s, it is j omega along this axis here, and along this axis it is the real sigma. Right, so we're going to give you a representation of Laplace, and it looks like this. You'll learn how to calculate this later on. But how do we get from this x of s into this plot? Well, all you need to do is to substitute s with different values along the whole complex plane. For each value that you substitute in, for example, if you substitute this value in, I guess this will be sigma equals to maybe this is 0, this is 1, this will be 2, and j omega is 0. So this is 2 plus j 0. If you substitute this into this equation over here, you'll get a value, a complex value. And you can plot the magnitude of the complex value, and for all this entire z-plane, you get a surface, and this is what we are seeing here. Alright, once we have this, then we are interested to find out when sigma is equals to 0. So this line is sigma, and when sigma is 0, we are interested in the surface that is being cut here, and we got this surface. Alright, So this surface is very interesting because this is a surface that is formed when sigma is equals to 0. And let's remind ourselves, when sigma equals to 0, this is the continuous time Fourier transform of the signal. So in fact, when we extract out, this is the magnitude of the continuous time of Fourier transform of the signal. So notice this peak here at minus 2 pi and plus 2 pi. Where are they? They are here. So this at this peak will be minus 2 pi, and at this peak will be 2 pi. Sorry about that. So let's see the figure again. Now I'm going to draw it in green. The peak here corresponds to the peak here on the right hand side, and where we are now drawing in yellow, these two points at minus 2 pi and plus 2 pi along j omega. This is the point here and point here, and we see that they are lying in minus 2 pi and plus 2 pi along the j omega axis. So before we end this discussion about continuous time Fourier transform, we want to remark that there's a conflicting notation. Why? Well, let's remind ourselves what the Laplace transform of f of t is. It's the unilateral transform is from 0 to infinity f of t e minus st. We remind ourselves that s is sigma plus j omega. Now, what we do is that when we say Fourier transform of f of t and f of omega, then this omega is put into here. We did not put j here because if we want to be like the Laplace, we should be saying Laplace transform of f of t is equals to f of sigma plus j omega. Now when sigma is 0, we can ignore that, and the notation leaves us with plus j omega. But you look at the Fourier one, he didn't put j omega, which was used in the Laplace representation. So there is this slight confusion, but the notations have become standard, so you have to remember that the Fourier representation do not use j there, or the Laplace does. I would also urge you to look at Brandon's video discussing Laplace transform over here, and in his video he explains it that the Laplace transform is the same as the Fourier transform of the signal x of t multiplied by e minus sigma t, where sigma is what we are interested in for all the sigma plus j omega, because Fourier deals with j omega, and all we need to do is to multiply the signal by e minus sigma t, and when we take the Fourier transform, it is equivalent to the Laplace transform. Okay, so please go through this video and it will bring you a lot of insight into Laplace transform.